Good afternoon, ladies and gentlemen. I would like to welcome you to another beautiful day in sunny Adelaide, but unfortunately I can't. It is freezing here today and it has been pouring with rain most of the day. It's fortunately not raining at the moment, but it has been just one of the worst winter days I can remember. However, enough of that. Let's do some maths with Gary. And today I want to talk about a study technique that I call the debrief. And Zoom seems to have lost my file. I haven't, but Zoom appears to have. So this is a study technique that I recommend students try for long and difficult problems. Now, the examples that I've got are mainly calculation type examples, and hopefully you should have a pretty good idea of what you're doing in that sort of a question. But this is a technique that really shines when you're solving some sort of problem that you didn't really know how to start. When you're studying a simple example, it usually makes a fair amount of sense. I can understand them fairly easily, but a really complex and long example, and they're usually too hard and long to memorize. And I'm not a fan of memorizing how to solve a particular problem, unless it's something that you do all the time, like solving the sides of a right triangle or something like that. If I rely too much on memorizing particular problems, if I come across a similar but slightly different problem, I may not be able to do it. Instead, what I do, instead of memorizing, is I do a debrief, I call it, quotes there they are, which essentially means a summary of the main steps in English. That's my native language, I don't know what yours is. And this takes advantage of the fact that the human brain is hardwired for language. So words are easy, but symbols are hard. And the process involves reading through the example, which I've probably copied out anyway. That's a really good thing to do, particularly with hard examples, copy them out. And as I go, I find ways to summarize the main points in English. And this helps me establish a roadmap to solving the problem. And so if I come across another problem, I've got a bit of a head start on figuring out what I have to do to solve it. If I just start writing down equations and relationships and so on, that might help me get to the solution. But if I can actually plan ahead, I've got a much better chance of getting a solution fairly quickly without going off in too many directions that don't make sense. So with that in mind, let's look at a couple of examples. Don't worry if you've seen the maths involved in these specific examples. And these are quite relevant to a couple of courses I teach. And one of them is just a problem that I picked out from, it's actually something that my daughter brought home from school. But what we're really looking at is the process of summarizing the steps in language, okay? So if you are one of my students in one of my classes, you will see a couple of these problems sooner or later. But even if you're not, it's not the maths so much that matters, it's the summary. So the first example is projecting an unknown vector in R3 onto the subspace W, spanned by these vectors. Now, if you don't know what vector projection is, basically it's kind of like taking a vector, putting it close to another vector and shining a light that's perpendicular to the second vector, saying, okay, this bit here is the shadow, so that's the projection. Now, when we project it onto a subspace, we've actually got to project it onto these basis vectors. So anyway, the calculation is not that important, it's the summary. So here are my steps. Here's my summary. The first thing that we need to do is make sure the vectors are orthogonal. These two vectors here, these basis vectors, have to be orthogonal. And if they're not, we would have to make them orthogonal. So I've taken a dot product here, a vector dot product, and that is 0, so they are orthogonal. Check, passes that. So my English language summary of that step is test basis vectors to show that they are orthogonal. Beautiful. If they weren't, I'd have to make them orthogonal. That's a whole different problem right there. But anyway. The next thing that we have to do is we have to find the length of each basis vector for use in a projection. You can't do a projection without using the length of the vectors. And so I found the lengths of those. And my summary is find the length of each basis vector. And so these steps are a lot easier to memorize than all of this stuff. Now, of course, that assumes that you know enough maths to know what it means to find the length of the vector. Now we project the unknown vector onto each of the basis vectors. And so here are the steps down here. And you can see here's my unknown vector x, y, z. I haven't actually specifically mentioned. I've got my unknown vector x, y, z. And this is the formula for projection. We dot it with the vector v1. We divide by the length of v1 squared. And that is the length of the projection. So that's not quite the length of the projection. And we multiply it. It's a scalar is what I was trying to say. That is a real number or a scalar. And then we multiply it by this vector v1. And so I go through that calculation and I wind up with this big, long algebraic vector. It's not a specifically known vector, it's an algebraic vector. And I do the same for v2. This is all one step here. Right? This big sort of cell, that's all one step right there. So I'm projecting v1 onto, I'm projecting the basis vector, I'm projecting unknown vector onto the basis vector v1, and I'm also projecting the unknown vector onto basis vector v2. And I get these two things, not great to work with, they're reasonably complex. But the summary step of that is project the unknown vector x, y, z onto the two basis vectors using the formula for vector projection. And I've taken the opportunity to write out the projection formula again. Okay? It's really important to write out your essential formulae more than once. That's just super helpful. It will absolutely help you remember that much better than if you just read it a couple of times. I'm a huge fan of writing for learning in maths. The more you write, the more you remember. So now we add the two projections together, and the result is the projection of the unknown vector onto the subspace. And you can see I've taken these two reasonably hideous vectors and added them together. And the answer could be left in this form, or the terms could be put over a common denominator. And I'm just going to leave it in that form. That's perfectly adequate. And my summary there is just add the projections together. And so when I want to review how to solve this problem, what I'm going to review first, and before I even cover the problem up and try it by myself, without looking at the answer, is test the basis vectors to show that they're orthogonal. Find the length of each basis vector. Project the unknown vector x, y, z onto the two basis vectors using the formula for vector projection. And add the projections together. And that gives me a roadmap for solving this particular problem. It's only a calculation problem. Hopefully it's something that I would understand how to do, because we would have done a couple of these. And we would have done some with known vectors in class before we actually tried something with an unknown vector. Here's my second example, solving a second order non-homogeneous ODE. And this is a second order ordinary differential equation. Again, if you haven't done the maths for this, it's more about the language steps. Okay? The point of this video is that hopefully you'll get an idea of how to do these summary steps and use them in your review and revision. So we've got an electrical circuit with a magnetic inductor, a resistor, and a capacitor, and some input voltage. A diagram would have been nice. Why didn't I put a diagram in? Would have been very helpful. Anyway, don't worry about all this, because as I tell my students, I'm going to give you this equation. Okay? I'm not going to give you this information and say, find the equation and then solve it. I'm going to give you this equation. might not even tell you all this information. And we want to find the charge at any time t. And charge is literally electrons passing a point at any moment. Sorry, that's current. Current is charge passing a point at any moment. So charge is really refers more to the charge on the capacitor. But anyway. So what are our steps? First solve this equation, Q double dash plus 100Q equals naught. And that's what we call the homogeneous version, where we've made the right-hand side 0. And I should say that. Homogeneous. Yeah, I'm trying to put that in. And so this is what we call our characteristic equation, right? So you'll look at that, Q double dash plus 100Q equals naught. That's where we get lambda squared plus 100 from. But again, if you haven't studied this, that's not important. You will come across this when you study this particular topic. What is important is that in words, it's just solving the characteristic equation. And if you learn this method of solving these ODEs, you will hear about the characteristic equation. You'll know what the characteristic equation is. So that's a perfectly sensible comment once you've studied this particular topic. And so if you get this solution to the characteristic equation, you will then know that this is going to be what we call the complementary function, or Q subscript C of T. Right? So you'll do that in class or by reading a book or whatever. And all that is that's your complementary function, QC. You can write it down or whatever you want. Now, the next step is to realize that Q subscript P, so QC is the solution of this equation if we make the right-hand side 0. QP is some solution of this with the right-hand side equal to 200 cos 10t, as it should be. And that's what we call a particular integral or particular solution. And I've just made a comment here that that is not going to work. We have to try A times T times cos 10t plus B times T times 10t. So my comment here is choose the particular integral, QP, bearing in mind that the usual choice won't work because it's part of QC, so multiplied by T. And if you have a look at this, here's my QP up here. And this is my QP, and you'll notice that that is basically the same, and so that's not going to work. And again, you'll need to study that topic to know why that is true, but it won't work because those two terms there are the same as these terms up here. And so the solution to that is to multiply by T, and then it will work. It will probably work. And if it doesn't work, multiply by T again. But again, you will study that in due course. Okay. So having done that, I differentiate QP. There's the derivative of that. I differentiate QP dash and find QP double dash. And the reason for that is I'm actually going to substitute all these things back into the original ODE. And so I need to know QP, I need to know QP dash, and I need to know QP double dash. And so my summary is just find the derivatives QP dash and QP double dash. And then I'm going to put them into the original equation. So, and that original equation was QP double dash plus 100 QP is equal to 200 cos 10t. So there's my QP double dash. It is all the way up to there, up to this blue bit. Then I'm adding 100 QP, which is this red bit and this blue bit. And that has to be equal to the original right-hand side, 200 cos 10t. My English language summary is just substitute the derivatives and the function into the ODE. and I should probably say that's the non-homogeneous form of the ODE. And I've coloured these things to show that they will cancel out. And then I'm looking at my sine 10t terms, because this equation can only be true if the sine 10t terms on the left are equal to the sine 10t terms on the right, and if the cos 10t terms on the left are equal to the cos 10t terms on the right. So that's where I've got minus 10a is equal to 0. You know what I'm called? My button isn't done. So yeah, I've got this sine 10t term here, and the right-hand side hasn't got a sine 10t term. In other words, it's 0. So that's why I've got minus 20a equals 0. My cos 10t terms, 20b cos 10t equals 200 cos 10t. So there are my two equations. And I've just said equate like terms. I could expand that out if I wanted. I could say equate sine terms on the left with sine terms on the right, and cos terms on the left with cos terms on the right, and so on. But reasonably experienced at mathematics, equate like terms is enough for me. A equals 0, B equals 10. Solve for the unknown constants A and B. So the next thing is to write my QP of t. And the full solution, Q of t, is actually QC plus QP. Well, there's my QC, there's my QP. And so my summary is find QP and add the QC for the full solution. Now, if I put t equals 0, that's going to give me 1, that's going to give me 0, that's going to give me 0. So I know straight away that C1 is equal to 0. That was a really easy constant to find. And so I'm just saying, right, substitute initial condition, find C1. So there's my Q, and this is now I've rewritten the solution, but I'm now putting C1 equals 0, which I just found. And so of course this term just disappears. So I'm actually writing the rest. I'm finding the derivative. And so my English language summary is put the value of C1 and find the derivative. And then when I put t equals 0, I pretty quickly get C2 equals 0. So I'm going to substitute t equals 0 and find C2. And now that I find C1 and C2, I know that my solution is actually this. And so my English language summation is just give the final solution. And I think you'll agree that that is a lot better than trying to memorize all of this stuff. That gives me a roadmap for how to solve this problem. Now, that's okay, and it's a useful thing to do. But in my experience, where this technique of study really shines is in solving a problem that is not a calculation, it's an actual problem. You've got to figure out the method for solving it. If you're a long-term subscriber, it's a small joke because I haven't been going very long, there are no long-term subscribers. You will have seen this problem before. I did it in my problem-solving video, but I want to use it as an example of the debrief study technique. So we've got a triangle with angles of 60, 40, and 80 degrees. There's a point X, which is 5 centimeters from each vertex, and we want to find the length of each side. There's a diagram. And so my first step is to draw a diagram showing all information. And at the moment, that's pretty much it. We do need to include the information that we've got about length. So that's my next step. So I've put in some dashed lines from X to B. and my step there is add lines from the central point of each vertex and show the lengths. I haven't put the lengths in. They're all length 5, so that's not quite as important. If I was doing this on paper, I'd draw a big fat ass diagram and I would have lots of room for the lengths and the angles. So I didn't put the lengths in, but yeah, ideally I would. Let's put some angles in at the vertices. Note that each triangle is isosceles because it's got 2 sides of length. That's how to spell isosceles. Ah, dear me. I just sort of threw this together. The first 2 examples I had already. This one I just did just before recording. It's got 2 sides of length 5, so that side there and that side there are the same, and so that makes these 2 angles the same. I've got 2 sides of length 5 there, so I've got 2 angles the same and all the way through. So I've just named the angles at each vertex, remembering that they are isosceles triangles, and so these 2 are the same. These 2 are the same. These 2 are the same. This gives us 3 equations, and they are at vertex A, alpha plus theta equals 40, at B, theta plus phi is equal to 60, and at C, phi plus alpha is 80. And my comment is this is 3 equations in 3 unknowns. We should be able to solve it. We could use an augmented matrix approach, as in a linear algebra course, but we can easily manipulate these equations. And so my English language summary is use the known values of each angle to write an equation for each vertex with 2 unknown angles and a known sum. That's 3 equations in 3 unknowns. Okay. That's an English language summary of what I did. So then I've manipulated these equations, and I've got theta equals 10. And of course, you know, in reviewing this problem properly, you would take a really close look at what I've done with these equations, but the summary is just solve the linear equations. That's a linear system of, this is a linear system of equations up here. We know how to solve that. So my English language summary for that step is just solve the linear equations. And from here, we can use the law of cosines to find each side. Let's do one as an illustration. And my summary is to use the law of cosines to find each side of the original triangle. And that, of course, is the original triangle, which is the outside triangle. So I've explained AXC. We've got those 2 sides and those angles. So our angle at X is 120. And there it is. And of course, if you were solving this problem for real, you would, of course, do the other 2 sides. So that sort of summary is much, much easier to remember and work with. And so, and this is the sort of thing that might help you map out a solution to a similar but different problem if you come across one involving a triangle. So that's where, again, where it really shines at solving some serious problem that you've never seen before, and then giving you a roadmap for that. So not only will that help you solve the same or very similar problem again, if you come across it in some assessment situation or some other context, but it will also help you verbalize a procedure for solving a different problem. It will give you a sort of an aerial view of the problem, and you can see, oh, well, if I do this, and then I do that, and then I do that, and then I go there, I might actually get the answer. And that's a really, really helpful thing to do. Okay, guys, I hope this has been another very useful video for you. As always, feedback is welcome in the comments. Good luck, stay calm, and keep studying maths. All right, bye for now.